All right, good morning. So this morning we'll kick off with WAN concepts. In this, we will be discussing how to interconnect various sections of our network over different locations. So we'll discuss how WANs operate, the traditional connectivity options versus more modern options, and then have a look at internet-based connectivity options provided to us today. So what's the purpose of a LAN or a WAN? So LANs provide networking services within a small geographic area. So basically within the same location, whereas WANs provide those services over large dispersed locations. And what we need to do is to be able to have a method of making it so that what we do on a LAN, we can expand across to a WAN. So we need to interconnect remote users and networks and sites together into a common network that everybody can have access to. Pretty much like what we do in a local area network, allowing users to connect and have access to common resources and provide high-speed bandwidth. We need to interconnect all these local area networks into one larger interconnected service where we can manage all of our enterprise services across all of our locations. Now, these WAN services do come at a cost because we need to engage an external service provider to provide all these links to the sites for us. Now, those links will be a combination of low to high speeds and over varying distances. So a private WAN, we can control our service levels. So what we're guaranteed to have as far as connections between our sites. It gives us a more consistent bandwidth and have constant security that is applied by our organisation. Whereas a public service, such as being provided by an ISP or our telecommunications company, the service levels and bandwidth will vary depending on how congested their networks get. And we cannot guarantee the security levels within those organisations. So the topologies that are used to connect sites together can be point-to-point, hub and spoke, dual homes, fully meshed, or a partially meshed alternative. So it's generally not a one-stop shop as far as these topology types are concerned. It's normally a combination of these topologies that WANs consist of. So point-to-point is where we interconnect two locations with a dedicated connection. Now this can be at layer 2 or via a VPN. Okay, so there's various ways of doing a point-to-point technology, but the traditional one is using a layer 2 transport service, such as a leased line or something like that, that provides that connectivity. Hub and spoke is where we split the service through the service provider and go in multiple directions. This is done using multiple types of technologies and different protocols. But basically we have a single connection to each location, and they all connect in a center location, which is the service provider or the cloud. Now, this type of communication has multiple single points of failure because we only have a single connection to each router. Typically speaking, what we're doing is we're using this hub as a central point that all communication comes in and out of. So for spoke A to communicate to spoke B, it has to come through our hub location before coming back out to spoke B. So although you would think the hub would be in the center of the cloud, it's actually on one particular side of the service where all traffic goes through to get. So the hub is the gateway for everyone. Dual home, this is where we can have multiple devices in the same location, providing multiple links to each of the spokes. This provides some redundancy, and we can have some load balancing and so forth capability through that. But because we have a duplication of equipment and links, it's more expensive to implement and requires more complex configuration than a single homed solution. Fully meshed means every site is interconnected to every other site. Partially means that not all sites are interconnected to every other site. So the names sort of provide that explanatory. So what we do is we sign a contract with our service provider, and this contract is known as a service level agreement. And basically what that says is what our minimum service that we're going to pay for is and what our maximum service is. So what it does is define the scope of service being contracted to us. So that is a minimum amount of bandwidth with a top level of bandwidth. So if we sign up for a link and we go over that, we've got options to what they can do to our traffic. One of it is they can drop it. Another one is they can bill us at extremely expensive rates. Most companies sign up saying they will drop excess traffic. And this means we set up filters so that we don't go over our top limit, and the consequence of them not providing that minimum service is they have to compensate us for it. So unlike our home connections with our service providers, we sign up to a service and our service is a maximum of up to. All right. So if we sign up with a 2 gig limit for speed or whatever it is, we get up to that. So whenever we sign up with a service provider in a domestic contract, they provide us up to that service level. We have no minimum service level with that provider. Now, some enterprises, depending on the requirements for redundancy, may sign up with multiple carriers to provide redundancy with their WAN connections. Now, one of the solutions for that secondary WAN supply is it might be on an ad hoc basis. In other words, if their primary connection fails, they'll use a secondary connection from a secondary provider, but has a higher cost due to it not being used for the majority of time. So they have a very low standby cost, but get charged for when they actually need it. So there's multiple options that carrier connections can provide, and the service level agreement is what defines all these options and the costs associated with them. So, as with everything else, requirements of networks change depending on the company's growth. They need to be able to meet day-to-day operations of a business, and as such, they need to be able to adapt and grow as the company changes. Network designers and administrators have many challenges to merge all these various technologies, protocols, and even service providers together to give a single, fully functional network to the enterprise. All right, now we need to look at all the requirements and the best solutions to optimize the network design to suit the company requirements. So a small network, we will have a single connection to the outside world, and we could be sharing wireless and switches together using a digital subscriber line to connect to the internet, and we can have support contracted out to our outside provider, such as the service provider of the internet. So depending on the size, depends on how we start out. As the company grows, you might move into a larger building and might require several floors of that building. So the way we now design that is with a campus network, and we have multiple departments, each segregated into its own functional groups, and they all share a common firewall before connecting to the internet. We now have an in-house support team to maintain our network and all of the peripherals contained. Then, as the company evolves and grows again, we expand across multiple locations, and this is known as branch networks. So this is where we start interconnecting our remote sites into our headquarters or central office, and we can have different ways of doing this. If we're in the same metropolitan area, we can use a MAN, which is a wide area network that provides high-speed connections within the same city. Next is where we go around the world. So this is a distributed network, and we now have offices all around the world, and we use site-to-site remote access using VPNs that allow us to quickly and easily set up connections between the sites, and also allows us to have remote connections for employees coming into the enterprise using secure networks, protecting our information in transit. So how does this all work? Well, we have standards which are controlled by the usual suspects. Okay, I'll let you read them. They're the usual ones that we've talked throughout all of networking. And they set up the standards that focus primarily on the physical and data link layers of the OSI model. So they tell us how the medium is going to talk to each other. So this is the protocols of how we actually physically transmit the ones and zeros. Then we go to the way we're going to access that media and the various ways we're going to represent that information. And we start looking at protocols such as our DSL, cable, wireless, Ethernet, point-to-point protocols, frame relay, ATM, so on and so on. So as technology develops, the options of how those media and protocols interact will change. But generally speaking, when we're talking about enterprise level WAN connections, we have common items, one of which are data terminal equipment, DTE, data communications equipment, DCE, customer premises equipment, point of presence, and demarcation points. Now, what this is a set of equipment that we use to represent who's providing what. So the demarcation point is generally located at a point of differing service. So on this one, the service provider is on the right-hand side. So the service provider is responsible for providing and maintaining all of the network up to and terminating at the demarcation point. The enterprise then takes over the responsibility of maintaining that infrastructure from that point on. So depending on where you are in the world, depends on where that demarcation point terminates. If you're in the US, it's on the boundary of your property. If you're here in Australia, it's within a point of presence within the building. So they bring all their cabling up into a point where they hand over control of the infrastructure. So if we're talking about a home, it's on the exterior of our houses here in Australia. They put a little box on the outside wall where they terminate their cable, and then we as owners have to take that cable and bring it into the house. If it's a business, it's generally a communications room within the building where all the various communication providers terminate their cables in, and then they bridge out from that demarcation point into the various locations in the building. Now, the first piece of equipment generally located in the building after that demarcation point is known as a DCE device. This is the data communications equipment, which generally is provided by the service provider. This is the device that changes the signaling so that the service provider can connect to your equipment, which is the data equipment, DTE, which is generally customer premise equipment as well, depending on your agreement. So when we talk about cables and DTE and DCE ends, what we're talking about, generally speaking, is we have a termination equipment here, and we have customer terminating equipment there. And the cable between has to have specific connectors to terminate against the DCE and the DTE. Now, generally speaking, the DCE controls the synchronization between these two devices as far as timing of the signal across these. So we say DCE has the clock, C for clock. So when we're setting up serial lines, we need to have a synchronization or heartbeat for the signals, and the DCE provides that signaling synchronization. Now, the other things we need to talk about is terminology. So the local loop is known as the last mile in some texts, is the cable between your termination point and the branch of your service provider. So wherever that telecommunications central office is located, now in Australia we call these things exchanges. They're Telstra exchanges, or Optus exchanges, whatever the telecommunication provider's location for their equipment is. This is where they bring all of their cables together from the suburbs into one location and then connect them to their toll network. Now, the toll network is their backbone of their network. So all of their exchanges interconnect together onto the common backbone of their network, which provides you with your service. Now, it's called a toll network because they charge you for the use of that network. They charge you a toll. The backhaul is what interconnects all of these sites together, and the backbone network that provides all this connection is a large capacity, high throughput network, because they combine all your individual accounts together and use the same infrastructure to interconnect to every other location. So they've got a lot of traffic. So what types of devices will we see in a wide area network? We'll see a modem. Now, a modem comes in many shapes and sizes. Now, a modem is what connects our site to their site, and it modulates and demodulates the signal in the subscriber preference. So depending on what type of service you connect, depends on what type of modulation service you need. Now, this could be voice, DSL, cable. All of them are referred to as a modem. Now, today, these modems don't generally exist as a separate device. They tend to be inbuilt into a single multifunction device. Next, you have a CSU-DSU. This is a device that was used to connect leased lines, and they provided a digital service to an analog service, if you like. If you were connected via optical service, then you needed an optical converter to convert from fiber optic to copper, which is generally what was used in your local area network. Then you have the various routers and access devices, such as wireless routers or access points, and then you have the actual core WAN devices. These are generally multiple high-speed routers or fast big layer 3 switches. So let's have a look at the traditional serial communications. Now, most forms of serial communications either happen either in serial or parallel. Now, what happens is, very simply, and this used to be animated, probably still is in the actual online material, but basically with serial bits, each bit is transmitted one after the other, so B1, B2, B3, one after the other across the cable. Whereas parallel, all of them are transmitted at the same time, and you have all 8 bits being sent at the same time. Now, what happens is this system, these bits can be out of sequence. In other words, they're not exactly arriving at exactly the same time. This occurs because there are different physical characteristics in every wire. The resistance, the connectivity varies, the speed varies because of all the impurities within the media. So over time, they become out of sequence and are not all recognized as arriving as the same set. So to limit this issue, parallel cables are only used over limited, i.e. very short distances. So for long distance communication, we use serial communications. Circuit switched. So this is where we basically have the history. Just remember that networking is a form of telecommunications. All of our modern day computer networks derive their history out of the telecommunications era. So circuit switch is basically where we dedicated a circuit from point A to point B so that users could communicate with each other. These were a dedicated connection, and when they started out, they would actually physically dedicate copper wires to that core. As the time's gone past, it's now a virtual connection through your service provider that starts at point A and ends at point B. Now, the most common circuit switch technology still in play is your public switch telephone network and your integrated services digital network, ISDN. Packet switched is where we allow the IP packets to be switched on a first in, first out type basis. So we have a more robust redundancy throughout the network, as the ability to use the same cabling shared across multiple cores is enhanced. So this allows the infrastructure to be built to cater for more services, which makes the overall expense cheaper compared to circuit switching, and is more flexible. So technologies that use packet switching is Ethernet WAN, i.e. Metro, MPLS, frame relay, ATM. No, I'm not talking about the cash machines down the street. I'm talking about asynchronous transfer mode, which is the big cousin to frame relay. So what we migrate up to, that was generally, a lot of that was copper-based. Now we come up to the superior use of fiber optics for long distance transmission, which means we can get further with lower attenuation and less interference. And the common ones that provide this is SDH, synchronous digital hierarchy, and SONET, synchronous optical networking. Okay, so they are the two main ones for international communications. And they generally use dense wavelength division multiplexing to increase the capacity over their old standards. Now, traditionally we broke it up into two modes, dedicated or switched. Dedicated lines, we basically leased a line from a telco. We used to go, okay, we want to lease a line from Melbourne to Texas, to Houston in Texas, and that line would be available to us and only us 24/7. That used to cost an arm and a leg and a major organ. So switch-based allows us to provide more flexibility in that we had the ability to plug in from more locations, as we didn't have to make sure they had a spare line that we could lease. We could use the existing infrastructure and allow the service provider the freedom to intermix between those lines and maximize the use of their infrastructure. This allowed us to decrease our costs and provide us with more flexibility. Lease lines were given to us in fixed capacities and were generally based on the bandwidth required and the distance between the two endpoints. Now, depending on the capacity required over the copper, we had two standards, the T carriers and the E carriers. T's were North American, E's were Europe. Now, in Australia, we used the E standard, and that meant a standard E1 link would support 2 megabits per second, whereas a T1 standard over in the US would be 1.5 megabits per second. So we have different maximum capacities within the various standards. So advantages, disadvantages of having lease lines. Advantage, it was a simple point-to-point requirement. it had high quality and high availability. Disadvantage was the cost and basically no flexibility. Circuit switch connections came about because providers wanted to make better use of their infrastructure and to maximize their profits. So we had use of the good old telephone network. So we could use dial-up, which meant we had a 56K modem, and that 56K had to fit within the 64K channel that a standard voice call over a telephone network was allowed. So we had a limit of how much data we could push in there, because we had the data we wanted to transmit, and then we had to allow for overheads on top of that to keep the call running. Now, integrated services digital network came about that allowed us to carry signals in a higher capacity, and basically what we did was combine multiple voice channels together. And depending on the standards used, we would bundle voice channels together. Some of them we would use our control messaging inside each channel, spread over multiple channels, which was known as in-band, or we could use out-of-band control, and that meant that we had a dedicated channel specifically just for the management and coordination of all the other channels. Packet switching came in frame relay and ATM. Now, generally speaking, frame relay was generally used for 2 meg links or below, and they used a permanent virtual circuit that identified the various connection points, and they used a data link connection identifier to identify each of those links. Now, generally speaking, ATM can be also referred to as cell-based architecture, as each frame in the ATM model is exactly 53 bytes in size. Okay, so we used to plug frame relay in to ATM. So you would come in your last mile into the exchange, and the backbone would be an ATM connection where they would plug in all of these frame relay connections into the much faster and controlled ATM. Now, ATMs are basically being replaced with the faster metro and internet-based solutions, which we'll talk about in a little while. So, as demands of business have exploded in computing power and the requirements to be online and connecting to all the businesses around the world, the technology to make that happen has also changed. So we have seen technology change, adapt, and develop new ways of communication across various elements. So we now have full use of optical, telephone, coaxial, satellites, Wi-Fi, and even mobile technologies to provide local loop connections that we all are familiar with and make use of today. Now, we still have dedicated connections, switch connections, and we now have internet-based. So things have changed a little bit depending on the solutions that we want to use. Now, leased lines now generally consist of fiber optic cables, and what they do is they pull in large optical cables and don't use all of the individual strands within that cable, and this is known as dark fiber. They then lease or allow you to purchase these dark fibers within their cables for your use. Metro Ethernet and MPLS are now replacing the packet switched technologies of frame relay and ATM, and they enable us to do very funky stuff. MPLS is like VLANs on LANs, but on a bigger scale. So if you want to have a brief understanding of what MPLS is, think of .1Q, but on steroids. They use tagging pretty much like we do in VLANs, but on a much larger, more complex scale. It's a very interesting protocol. Then we go to our broadband solutions, which basically is VPNs. So we can use VPNs over wired or wireless solutions and various technologies within those. So how do we distinguish all of these? Well, Ethernet WAN has gone by many names. Metropolitan Ethernet, Ethernet over MPLS, virtual private LAN services, you name it, it's out there. And there'll be more changes as every day goes by, because as you're aware, courses are written, technology keeps changing. So you'll probably have different technologies out there now that aren't even listed on these slides. So the benefits of having Ethernet WAN is cost and administration. So it doesn't cost us as much and it's easier to administrate. It's very easy to integrate into our existing networks because it's all Ethernet, and provides us with greater productivity solutions across the enterprise. Multi-protocol label switching, as I said, is VLANing on steroids. So it allows us to support multiple clients, each of which can have a different connection into the MPLS cloud. And we basically have a customer edge device, which is where we connect in, and we connect to a provider edge device. Okay, and what that means is we have a great range of connection types. So we can use DSL, cable, Metro Ethernet, fiber solutions, whatever we want, we can connect to. Okay, so we can connect two devices together using some form of technology. we can use MPLS over it. So how does MPLS routers and label switching routers? So basically, routers forward based on a table, which basically says, I have a circuit or a label that comes in, and it's got a little chart that says, okay, label 5 comes in to my device. All right, so we come here, for example, we come from this right-hand device into the cloud, and that's connected via virtual circuit 5, so it's got labels 5 on it. That will tell it where to go to. So I'll go, okay, I'm label 5, so I've got to go to this device, and my label between these two devices is 10. Gets to here, it's got a little chart saying I've arrived on channel 10. Channel 10 connects to here via channel 20. And then it'll connect to this end device on channel 5 again. These labels are only locally significant. They can be reused throughout the network, and basically these MPLS devices switched based on labels. They're equivalent to network addresses, and they can switch between the VLAN, these tags, and forward traffic based on those tags. MPLS provides full quality of service support, filtering, redundancy, and VPN services. It's a very flexible solution, and there are dedicated courses just on that protocol. It is a very interesting protocol all by itself, if you're really a nerdy type person. So, internet-based or broadband VPNs come in wired and wireless options, and I won't bore you to tears with what's the difference between wired and wireless. I think you know that by now. Digital subscriber lines is high-speed, always-on connection that basically worked over telephone lines. So what happened with DSL is they used frequency above what was used for telephone services. So a lot of techs would call POTS, plain old telephone service. All right, that's its nickname now. So I think it was originally, I just can't remember now, it's been so long. Post office telecommunication service or something, telegraph service. That's bringing back the old grey matter. Now, ADSL uses the frequencies above, and it's divided from upstream and downstream. And they're in little chunks of frequencies or channels, and they combine different frequencies together to give you your different speeds upstream and downstream. Now, DSLs connect to the exchange or central office and are combined together before moving upstream. Now, when they enter the central office, they need to have the voice and the data separated from each other. So the voice connects to the PSTN network, and the data goes off on what we know as the internet. Okay, it's not a shared medium. We have distinct frequencies just using the same cable. Now, The DSLAM is the device that allows us to separate those frequencies into their discrete communication channels. Quite often we would use point-to-point protocol over DSL between the service provider and us, and this would be known as Ethernet point-to-point service. So PPP over Ethernet, and we would have a client, and that client could be a router or a modem, depending on how you are set up. So this allowed us to have a dedicated communication between our service provider and our equipment. Cable TV came about first, and this was basically the history of this. Was the aerials or antennas were on the tops of mountains to capture the TV signals, and then they would be piped via this closed circuit of cable provider down into the valley, because the residents couldn't get TV service. That evolved into data over cable service interface specification, DOCSIS, and it allowed high-speed data over the existing cable network. So what it does is it uses different frequencies to provide the channels. And again, doesn't matter whether it's optical or coax. Most of the time it was coax down the streets and to the individual houses. And what happens is we have a head end, which is the management system, contains a database with all the clients and the specifications of their subscription. And this head end would then separate what was telephone, TV, or data out and connect it to the various networks. Now, the downside to cable was the more local subscribers connected to this cable meant that there was less bandwidth available to individuals. So the more that joined, the lower the bandwidth became. Basically, they would oversubscribe the service. Optical fibre now comes in various flavours: fibre to the home, fibre to the building, fibre to the node. So fibre to the home, basically you have a fibre coming into the residence. Fibre to the building, they bring the fibre connection into the building, and the building's owner was responsible for divvying up the service within the occupants within the building. Fibre to the node is where we have fibre optics running down the street, and then they would branch out from fibre optics to more traditional coax or telephone wires to connect to the houses. So basically, fibre to the node makes use of the more traditional type of telephone arrangement, where you had copper running into the houses, and what they've done is they've brought the backbone of the optical network down into the streets. So you'll see a little box on the nature strip where they divvy up connections to all their houses using copper. It's a cheaper solutions in that they don't have to run fibre optics to every single household. They can make use of the existing copper and save some money. Wireless comes in all shapes and sizes. We've covered this multiple times. So we've got metro-based Wi-Fi run by the councils, mobile technology, satellites, and white max, which is microwave. And we've already looked at the multiple various technologies used in wireless, so I won't go over them in detail. So VPNs allow us to mitigate some of our security concerns about using a service that is provided to us by a third party. This allows us to encrypt our messaging and transmit it across public networks. These are routed the same as normal IP traffic, but their contents are encrypted. So the benefits of using VPNs is we don't have to have dedicated WAN links or banks of modems for individual dialing. It uses advanced encryption and authentication protocols to protect us and the data. It's very scalable, and it's fully compatible with any broadband technology. So we use these in two main forms. We use a site-to-site VPN where we configure it to encrypt our data in transit between the routers, and clients do not know that this is occurring at all. The other one is remote access, where the user initiates the connection so they know that they're connecting via VPN. One of the things that a lot of people assume when they're connecting to their bank for it is that the HTTPS is as best as it gets. But the bank can actually provide a VPN solution that is even more secure and allows the users to authenticate with the bank. So VPNs set up a client on the device and they can dial in using whatever technology is available and authenticate with the device at the destination. Homing comes in very many different ways. Single home, pretty straightforward, single connection, one link. Dual home is where we've got dual links. Multi-home is where we have multiple connections to different ISPs. And then they now include dual home, dual multi-home. So dual links to two separate providers. So that is 4 in total, spread across 2 service providers. Again, we're going through the same list of broadband solutions as were previously, so I'm not going to spend any time on this one. We've already talked about all of these factors. So we have some activities for you to do, some labs to do, so you can have practice of looking at these connectivity options. So in summary, We introduced the concept of wide area networks and how they look. Basically, the logical topology is used, point-to-point, hub and spoke, dual home, fully meshed, partially meshed, and the fact that most networks will use a combination of those on an enterprise level. We looked at the fact that enterprises make contracts with their service providers, and these are known as service level agreements. We looked at the various uses of virtual private networks to secure communication between locations. We reminded you that the usual suspects are in control of WAN standards. We then went through the standard protocols for optical fiber and broadband. We then had a look at the difference between serial and parallel communication. We discussed the differences between circuit switched and packet switched. We had a look at the history of wide area networks that came out of telecommunications. So everything was based on dedicated voice channels, which were 64K voice channels. So the standards that came out of that were about trunking voice calls and increasing the throughput of voice calls through telecommunication providers, and how this has evolved into providing data services in ISPs now. We looked at the way DSL, frame relay, ATM technologies were offered to provide those original services, and how they've been keeping up with technology changes with Ethernet WANs, MPLS, and adopting different methods to provide connectivity as technology changes. We looked at how the standard technologies that we use to connect to service providers now provide us connections to various sites of our own around the world, and that we can use VPNs to tunnel through these public networks, securing our data in transit, and allows remote users to connect to us in a secure manner. And we had a very brief look at the various ways an enterprise can connect to one or more service providers to provide redundancy, whether it's a single link to multiple service providers or dual links to multiple service providers. And this brings us to the end of this presentation. And this is the point where I ask if there's any questions, where you have the deafening silence as the response, as usual. All right, so that is the end of chapter 7.